Hi guys, my name is Ivo and I'm from mytestedasp.net. First, a little bit about myself. I have been working as a CTO in a large software development team for a couple of years now, and I am also a part-time technical trainer for more than 6 years. Mainly, I'm teaching C# and JavaScript technologies. In my free time, I tend to write quite a lot of code. I create open source packages for the ASP.NET framework. For example, this package is a fluent testing library for the ASP.NET Core MVC framework, which allows you to have strongly typed and easy assertions uh, for various .NET components. Initially, I thought that this library will be finished in 2-3 months because I believed it was easy, but currently it has been developed for more than 3 years and I still have quite a lot of work to do. What is interesting is that during the development process of these packages, I had to open the source code of Entity Framework and the source code of ASP.NET, and frankly speaking, I learned quite a lot of stuff. I learned very interesting C# techniques, and I decided to start this channel to share my knowledge, and hopefully you will learn something in the process. Take a look around, you can follow me if you like. You can subscribe to this channel. I plan to release 1 or 2 videos weekly, and there are many interesting things to come. This video will be about expression trees, introduction to expression trees, because in my opinion they may help you optimize your code, or they may help you being more lazy, because we all know that programmers like being lazy. The expression trees are kind of interesting technique, which it's interesting that not a lot of people try to learn them or try to understand them, because at first they seem quite difficult and quite strange, but in reality ASP.NET Core uses them and uses them to optimize some of their, for example, view rendering. Entity Framework Core uses them quite a lot, and let's dive into the code and you will see that they're actually not that scary. First, for most of my videos I will expect that you know the C# language in general, you are familiar with object-oriented programming, and you are familiar with web basics. For example, if you can create a simple block application with the ASP.NET Core framework, these videos will be perfect for you. Okay, let's start. For this video, you will need to know what delegates are. You will need to have a basic understanding of the C# func and action classes, delegates, sorry, and additionally you will need to know a little bit of reflection. If you're not familiar with either delegates or reflection, or if you're feeling that you know what it is but you're not quite sure about your knowledge, let me know in the comments below and I will make sure I will create a more introductory video about delegates and about reflection. Just let me know and I will create one. First, let's make a quick summary of what delegates are. I will need a class, my class. I will write some method here, my method. Let the method receive number and text. and return some result. Then I will create one property, and we're going to use this class in our expression trees. Now let's create a delegate. As you may already know, delegates are just a pointer to a function, and you can pass it around, you can save it to a variable, and the easiest way to create a delegate in the C# is by using either func or action. Action is used when the method is void, when the method does not return any value, and func is used when the method returns something. Okay, for example, if I want to store this method in a delegate, I will have to write, okay, the method is in the my class, and the method returns string. Class goes to class.myMethod. That's one way of doing it, but it's the easiest way. I can create a pointer to that method, invoking it here. And I'm not going to um, show you a lot of details about the delegates because as you already know it, but as I said, you can always write down in the comments that you will need further explanation. Okay, I created a delegate which calls this method with these two constants, one number and one text, and I save it to a variable. This variable is like a normal variable. I can pass it around, I can give it to another method, for example like this. It needs to be static. Another method, func. So essentially a simple delegate using the func or the action is a storage of a method. We can save a method call, for example, to a variable, and this variable can be used again as a method. For example, this function here tells me that I need to provide my class instance and it will invoke something. So if I create my class instance and pass it here, I can invoke the delegate with this variable. Okay, I will get the result and print it. I received exactly what this method returns. And that's cool. I can create another func, for example, receiving my class and returning bool, and that will be the property, for example, from my class. Okay, these two are delegates, these two are actual functions. Another simple example of the func is, for example, if I want to save a function which gets two parameters and returns the sum of those parameters, I can write it down like this. So essentially I created a function, a method, that returns the sum of two numbers, and I saved it in this variable sum here. Remember, if you're going to use funcs, the last parameter describes what the function returns. So in order for this variable to work and in order for me to be able to save some function in this func from two ints, I need to have a function which have two inputs of integers and one input and one output of integer. For example, if I write it like this, it won't work because true is not int. So if I want to make the delegate work, I need to mark it as bool here. The action is the same, but the action only has, it's a void method, it doesn't return anything, so I can only provide inputs here. And the syntax is something like this. As we can see, this method does not return a value, it just prints something on the console and the method receives two input parameters. Okay, that's cool. That will be all I'm going to show in this video about delegates. I'm now going to show you expression trees, which look the same, and people may think that um, they're essentially the same thing because, for example, if I write an expression, I will explain it in a minute using system link expressions, and if I create the same func in the expression, the code look exactly the same, only the variable is not of the same type. So if I want to create a func and an expression of func, the code may look exactly the same, but there's a huge difference. This is the reason why when you create and use link extension methods, system link, there are two overloads of each method. For example, if I have a list of ints and if I want to filter it, if I examine the where method, I will see that currently it expects a function which receives an int and returns a bool, exactly this function here. Okay, but if I'm using entity framework databases and I'm using asqueryable, essentially my data storage is iQueryable, not IEnumerable, the where extension method now expects an expression of func. And there's a huge difference. Although the syntax may look the same, because I didn't change the where method, both funcs and expression of funcs work the same, are written in the same manner, they're very different. And now I'm going to explain you why in Entity Framework Core you need to write expressions, although you may not know that you are writing expressions. A lot of people don't understand the difference between a func and an expression. I'm using Entity Framework as an example, not because it's necessary. As you can see, this console app doesn't reference Entity Framework, but most people use expressions in Entity Framework and will be familiar with this syntax. That's why I'm using it as an example. Okay, now let's see the difference between the expression and the func. First, I can invoke the func. If I provide this my class here, I can invoke it, and that's kind of okay. I will receive the result from this function, and that's pretty much it. If you check what you can see here from the function, you can invoke it, which is essentially the same as writing it like this. There is no difference between the two syntaxes, and you can get a method info, which is method info from reflection. This method info class is from reflection, and for example you can analyze the name, but that's not very useful because this is an anonymous function. This one is created here, it's an anonymous function, and the name is something strange. It's a unique name, but it's not something we will recognize. So essentially the func properties are not that interesting. If we see expressions, on the other hand, you will see that we cannot invoke that. I cannot write it down like this. That's not possible because expression trees are not functions. They may look like one, they may look like function, but they are not. You cannot invoke it. And if I try to see what kind of properties I have here, there is no invoke. Also, there are other properties, for example, node type, body type, and so on. I will show this in a minute. But the essential difference is that the functions and the expressions are different. With that, the function can be invoked and the expression is just a data structure representing code. What I mean by that is I can analyze this code and I can extract parts of it and analyze them further. For example, I can try to examine the expression and I will see that it's a lambda expression. Here it is, I have a lambda expression. I can see that I have a parameter c of type my class. Then I can see that the body of the lambda expression has a method call. This method call is my method, this one. Then I can see that my method is called with these two constants, 42 and my test.asp.net a string. So essentially the expression trees are data structure representing code, and you can analyze it and extract information from it. With the func you cannot do that. This is why when you use normal lists, like I showed you previously, when you use normal lists and you call the where method, you pass functions, because normal lists can be iterated for example, enumerables, and these where filters will be executed on the list directly. But when Entity Framework Core or Entity Framework 6, for example, wants to translate this syntax into a SQL language, for example, or any other database language, it needs to analyze what you are trying to do. For example, if I have list of strings, as you can see, when I call text goes to text.length greater than 0, this is using a normal function, because lists can be iterated by using the enumerable interface, and this function can be invoked on this list directly. So essentially the C# language invokes this function on the list, on each value in the list, and then returns some result. But when we are using data storages like SQL Server, for example, we cannot iterate them directly because the data is not in memory here in our program. It's somewhere in the SQL Server. Entity Framework needs to know how to pass a SQL function trying to find length greater than 0. So Entity Framework essentially tries to extract information from your expression tree you are providing here and translate each small part to the native language of the database. For example, from this expression tree, Entity Framework will extract that I'm trying to compare the length of the strings. It will extract this value and it will extract the operator here, and we will translate that to the SQL language. And this is one of the purposes of the expression trees. You can analyze the code and you can traverse it like a tree structure. That's why it's an expression tree. The other purpose is a little bit more advanced. I will show a simple demo, but we're going to focus more on the analyzing in this video. In the future, I'm planning to create a more advanced C# expression trees tutorial where we're going to create more code on the fly, but for now let's focus on the basics. Okay, why it's called an expression tree? Because essentially every code is a tree structure. For example, the root of this file is the file itself. Then we have a child which represents the usings. Then we have a single child which represents this using. We can go even deeper. Each semicolon represents a child, but let's not go that way. Okay, then another child is the namespace. Then this class is the child of the namespace. Then this method is the child of the class. Then this method has a child arguments. This method has statements. Each statement is a different type of statement. For example, this is variable declaration. This is instantiation of a class. This is again variable declaration, and so on. So every code can be represented as tree, and expression trees are no different. Let's examine this one. I have the root of my tree, the whole lambda expression. One of the children is the parameters of the lambda expression, so essentially that's the parameter c, which is of type my class. Then another child is this method call. So we have my method call. Then my method call has instance on which is called. The instance is the parameter c. Here it is. Then my method call has arguments. I'm not writing very pretty, but I guess it's okay. And these arguments have two children, the constants. So essentially that's a tree structure. We have the root, we have two children, one of the children has another two children, and one of these children has two more children. So as with every tree, we can traverse it with a recursion. If you're not familiar with recursion, it will be very difficult to understand the next method I'm going to write, so it's better for you to learn it from somewhere and return to this video. Okay, we have the tree and we can analyze it. How to analyze it? We can analyze the tree by using the base expression class. The base expression class represents all kinds of expressions we can write, because a lot of expressions can be written in the C# code. We may have a constant, we may have a method call, we may have a property access, and so on. For example, this expression, basically the same as this func, represents a property access. So when I traverse the expression tree, I need to check what kind of expression I'm dealing with. Is it a parameter? Is it a lambda expression? Is it the method call? Is it the constant? And so on. Is it the property access? Each expression provides a way to check its type. Expression tree types are C# expression types. C# expressions are actually quite a lot. You have goto expression, which represents a goto statement, for example, in loops. We have an index expression, which represents getting or setting an index. We have lambda expression, the one we saw earlier. We have member init expression. The member init expression is this one, my property equals true. That's a member init expression, and so on. We have different types of expressions. Do we need to know them all? No. I'm not familiar with all expressions. I'm familiar mostly with the expressions I have been using, but I know how expression trees work, and if I need to learn a new expression tree type, it will be quite easy, and this is the knowledge I want to show you here. I want to show you how to understand expression trees, not how to remember all type of expressions. That's kind of wrong. Okay, let's take a quick look. How can I analyze this expression, for example? This expression, if I see here, has type, node type, body, and some other properties, for example, parameters. If I hit the debugger, I can analyze the expressions. For example, I can see that this expression represents the whole lambda expression. If I expand this, I will see that it's a lambda expression, node type lambda. It has one parameter, the return type is string, and so on. Then, if I get the body, I will get only part of that expression. See, it's no longer the lambda expression, it's only the method call expression. The lambda is missing here, and if I analyze the body, I will see that it has two arguments. This method call has two arguments, so I can analyze that further. I can see which is the method. The method is my method from my class. I can see that the object on which this method is called is C, and that's correctly. So essentially, the whole structure of this code is saved in that variable, and I can analyze it. Entity Framework uses that for extracting the language specific, the language details you're using, and translate them to the database. Now, you may wonder whether this is actually useful somewhere in your application code. Believe me, it's useful. My next video, which will be released in a couple of days, will be about using expression trees in your ASP.NET application right away. We are going to use expression trees in our controllers, and believe me, it will be useful and cool at the same time. So bear with me. The expression trees are quite fun. Let's create a static void parse expression method, and we are going to parse this expression tree one part at a time. So in order to have a more abstract parser, I need to use the base expression class, and then I can say something like this: parse expression, parse it with this one, and then parse expression, parse it with the other one, prop expression. And what I can do here now is I can start analyzing with what kind of expression I'm dealing with. The normal usage is like this. If expression node type is some type of expression, for example constant, I cast it to a more specific type, constant expression. This is everything you need to know. From here on, it's debugging and analyzing the type of information you know and you want from this expression. So we have lambda expressions as the root of our expression tree, so let's start with that. Expression node type. If the expression is lambda, this node type property is on every expression and you can use it to analyze what kind of expression you are dealing with. It may be, for example, convert expression, that's a cast. It may be equal, that's the equal operator. It may be lambda. It may be new, for example, initializing an object, and so on. Here we have an expression which represents a lambda. So I will check that, and if that is correct, I will cast it, because the base expression class does not have a lot of information in it. It has node type, and mainly that's the most interesting part of it. So lambda expression. When I cast it, now I will have a more advanced expression in which I will be able to extract even more information. For example, I have the body of the lambda here, and I have the parameters of the lambda. So I can try to print the body, and if I run it, I will see that the body of the expression is printed on the console, which is actually the child of the whole expression. When I have the body, I may call the same parse expression with the lambda expression. This is a valid call. So essentially I will recursively traverse the whole expression tree. Next, I will check whether the expression node type equals a method call. Why method call? Because I have a method call here, I want to analyze that. And if it's a method call, I have to cast it again. Method call expression. Unfortunately, these classes and these node types don't have the same names. For example, lambda and lambda is the same, but call and method call are different. So you have to remember what the expression is or search it on Google. You cannot see what class this expression represents. You may try to get its type and see it, but it's not always relevant. So essentially I casted the method call expression, and let's see what I have here. I have a method, I have the arguments of the method, I have the object to which this method is called. So I can write, give me the method name. And I did something stupid. Let me see where it is. Okay. Yeah. The problem is that I'm passing the same lambda expression here, and what happens? It's a lambda expression, so this code executes again. And what happens? It's the lambda expression, and this code executes again. And what happens? So essentially I wanted to pass the body of the lambda expression so that I can continue parsing it. And if I run it now, I will see that I'm printing my method. What I did for now is I analyzed the lambda expression, then I analyzed the method call in it. I can do the same with expression node type equals member access, var member expression equals member expression, and I can print the member name. What's a member, you may ask? It's a property or field access. So member access expression is this one, when I try to get a value of a property or of a field. So if I run this, I will see that my parser currently extracts the method and the property. Let's extract these constants. I can even print the parameter method call expression, not here, the parameter is in the lambda, console write line lambda console write line method and console write line property to see what kind of expression we extracted from the tree. Then I can, for example, print console write line lambda expressions parameters name. This will print the C. So I have a lambda expression, the parameter is C, I have a method and it's called my method. Then the second lambda expression has again the parameter C, but it's a property and it printed my property. Let's extract the constants here. So the deal is exactly the same. Else if expression dot node type is expression type constant, I can extract the constant expression, and the constant expression contains the value here. So essentially what I can do here is I can print 42 and I need to pass the constants, but this code here will extract these two constants because they are essentially a constant expression. Okay, now in order for my parser to work, I will need let me make it a little bit prettier. What I will need here is to extract the method arguments when the expression call is uh, a method call. So what I can do, I can say method call expression dot arguments dot length not last dot count. I guess it's a read-only collection. Okay, I have the count. Then I can call parse expression method call expression dot arguments from I. So essentially I'm telling parse the arguments one by one, and these arguments will be constant expressions here in this case. So they will hit this code and they will be printed. Here it is. I'm analyzing my lambda expressions one part at a time. First the parameter c, then the method my method, then this constant, then this constant. Then I'm analyzing the second lambda expression, which only has a property. So I extracted everything from this expression tree, and I can use it whatever I like. Where this can be useful, besides entity framework, obviously. For example, a lot of libraries use expression trees to analyze your code. For example, mock. For example, my library. Let me show you a simple example to give you some context. For example, this one. My framework has to have the option to assert routing configurations in ASP.NET Core applications. So essentially, I want my framework to be very easy and very useful. So with 4 lines, I can assert a route. My routing configuration, when the user hits that URL, I want that URL to match this controller in this action with these parameters here. If I was using a normal function, I won't be able to extract this method name, this parameter. I will be able to extract the generic type, but that's not enough. So essentially, what I do here, I run the MVC route resolver, then I get the root values, and I analyze this expression tree here. I extract that the action name is action. I extract that the ID of the action is 1. I extract the controller type, and I then assert whether these values match and are the same as the values from the MVC route resolver. So if I didn't have expression trees as a feature in the C# language, I wouldn't be able to analyze this code and assert whether the route is working correctly. Another example is when I need to assert actions, and essentially what I want a controller calling an action. I want to execute an action with certain data provided by these methods, and I want to check whether the method has a valid model state, view back entries, it returns view with some kind of result, so on. But I want to invoke the method. If I use a normal func, this will actually work, because what I need here is just to invoke that action. I just need to invoke the method, which essentially the func will do for me. But if I want to assert attributes, for example, like this, my controller calling my action should have action attributes. I will no longer be able with a simple func to extract the attributes from this action. I won't have the method information to use reflection on it and extract the attributes and MVC filters. So essentially an expression tree is very useful here, because I can use the expression tree to see the method call, to extract the attributes from that method and assert them. And with expression trees is as simple as writing 3 lines of code to check whether the expression tree is a method call, to get the method, and to get attributes. Here it is. It's very easy to create such functionalities and features if you're building a library. Well, it's not only useful when you are building a library. As I said in my next video, stay tuned for it, I will show you how to use expression trees directly in your web application controllers, and it will be very cool, I promise. Okay, what else can we do with expressions? And what's the performance of this code? The performance is okay. You should not worry with performance if you analyze expression trees. These expression trees are already built from the compiler and you are just making if checks. That's fast. That's not something that's not quite that's not slow. That's my point here. Entity Framework uses expression trees. Yeah, it caches a lot of them, but uses expression trees, and they're not that slow. If you have a very enormous parser, the parsing may be slow because you're essentially doing quite a lot of loops, but the expression API, for example, this check here, this cast, extracting the parameters, that's fast. The only slow thing you can do with expressions is compiling them, and I'm now going to show you how to compile expressions, but first I want to show you that writing 42 directly in the expression tree and writing a variable equals to 42 is not the same thing. That's not a constant anymore, that's a variable, so this check will not work. If you see, I see property ID, I don't see the 42, I can't see that. So when I'm dealing with variables, like Entity Framework is dealing with variables, it's a little bit more tricky to extract the value. There are ways, there are simple ways and fast ways, and I am going to show them in my next video, because we are going to need this functionality in our controllers to extract variables. But for now, let's just remove the variable and write 42 here. I just wanted to mention that it's different, and writing variables in expressions are not constants. Okay, let's get back to that compile thing. What is compiling expression trees? Compiling expression trees is running compile. Each expression can be compiled to an actual code. For example, if I compile this, I will receive the function behind it. So from here on, I will be able to invoke that function. Here it is. Let me save the result and print it. So essentially, what I did here, I'm going to delete that to not interfere with our code. What I'm doing here, I write an expression, I analyze it, then I compile it, and I'm receiving the function this expression represents. And that's a very powerful way to create runtime methods and delegates without knowing their types. I will show it in a minute. here it is. The compiled method is working and I'm able to use it directly. So compile essentially converts a lambda expression, which is a data structure of code syntax, to an actual executable code. You can compile every expression and use it afterwards. The only slow thing about expressions is the compile part. This is the slow part of the whole expression tree saga. If you use compile, it is slow. It's not very slow, as we can see, it runs quite fast, but it's the slowest operation you can do on an expression tree. So the best practice here is to compile as less as possible, and if you have to compile, try to cache the result. For example, let's say I'm creating this delegate, then compile it, and if this delegate does not change in future executions of this code, I can cache it in some sort of a dictionary or something else. Doesn't matter actually. The idea here is that I want to compile as less as possible, and if the result from every compilation is the same, I should compile it once and then cache it somewhere in a private field, in a dictionary. Doesn't matter. I want to show you that this is the same with funcs, but if you write an expression like this, two expressions which looks the same, these are two expressions, so you cannot compare them. Although the expression type is the same, although the expression syntax is the same, for the C# language, these two are different syntaxes and these two are different expressions and they cannot be compared. So essentially this means that you cannot cache an expression tree directly in a dictionary because these two expressions won't be the same. The toString representation may be the same, but that's not always true. So be careful when you're using expression trees with dictionaries. You have to find another way to cache them if you want to cache them, and be careful when you're trying to convert them to strings. Not every expression tree will be able to be converted to an unique string. Okay. For example, if I convert this one, I will see it in a friendly manner, but if I print it like this, I will see some strange syntax. Expression trees playground program quas.id. What is this is essentially every expression tree which has data outside of it creates a hidden class with some sort of this structure, some class unique with public int id in this case. So when I create an expression tree with a variable, a hidden class is created to save the reference to this variable so that when we invoke or analyze the ID, we can get the value. That's how it works. So if I write two expressions, and for example the first expression has ID 42 and the second expression has ID 12, if I print it like this, I will receive the same expressions, the same expression representation. See, both expressions look the same, but essentially they are different because the first one has 42 and the second one has 12 as value of the ID variable. So if I try to cache the expression as string in a dictionary, I will hit a problem. Okay, let's return, and again the compilation is the only slow expression tree operation. You should be careful with it. If you're executing a lot of compilations, consider how you're going to compile them. Okay, and last thing I want to show you is creating expressions on the fly. That's more advanced. I'm just going to show a simple example here where we're going to create this expression without writing it explicitly. So let's start with that. We can create expressions by using the base abstract expression class. From here we have a lot of static methods which we can use to create code on the fly. Let's start with the simple basics. I need to create a constant which represents the 42. So the syntax is number constant equals expression dot constant, because I want to create a constant expression and I have to provide 42. Then I want to do the same with this variable here. So I will create text constant equals expression constant from this text. Then I have a method call. The problem here is that the method call is invoked on the parameter, so I need a parameter expression. Parameter, I need to provide the type of my class, and then I will provide the parameter name. If I hit breakpoint, I will see that that's exactly an expression which represents the constant 42. That's an expression which represents the constant mytest.asp.net, and that represents a parameter expression which is C and it's my class type. Okay, I created this constant, I created this parameter, and I need a method call. So call expression equals expression.call. As you can see, creating expressions is always from this base expression class. I just need to know what type of expression to use. Okay, the call needs instance on which the method call is invoked. The method call is invoked on the parameter C, so I will provide that instance. Then I need a method info, which method I'm trying to invoke here in the expression tree. The method info is type of my class, get method name of my class dot my method. This is the method I want to use. Since I'm using my class twice, I'm going to cache it in a variable. It's always a good idea to not copy paste operations, so because you will have a very small performance hits. It's very small, but you will have it. So let's cache it in a variable, and expression call parameter expression. It expects the method info, so I'm going to give it, and then expects the arguments. The arguments here are constant expression number and constant expression text. This essentially should create a method call with the provided data. Let's create that. and see for ourselves. See, we have the method call invoked exactly like here. And I created that on the fly. I'm creating a runtime code now. Great, but keep in mind that expression trees are very fragile, and if you're not creating a valid code, you have a lot of problems. You have a lot of exceptions. So this code here is not production ready. You need to make some checks to make sure the code is valid. For example, if I change the places of these two constants, I'm essentially trying to make C# invoke see my method with first with the text, then with the number, which is not a valid C# syntax because the method first requires an integer and then a string. So if I run that, I will see an exception. Expression of type system string cannot be used for parameter of type system int, and that's correctly because I'm trying to pass a string as the first parameter of the method, which is not the case here. So I have to return it like this. So currently it's working. What I'm trying to show here is make sure you validate our expression tree calls. And I have the method call, I have the parameter, now I have to create a lambda expression. So lambda expression is expression.lambda, and I have a generic version of this method which allows me to provide the function I want to compile afterwards. So I'm going to provide this function which receives my class and returns a string, which is essentially true because my lambda expression receives my class and returns a string from this method. So what I want to provide here, I want to provide the body of the lambda expression. The body is the method call, so I need to give this call, and then it needs parameters. The parameter is c. So I created the lambda expression. If we hit the debugger, we can see that the lambda expression is the same as the one here. And if I delete that and hit compile on this expression, I essentially created a function on the fly which can work for me. See, I created a function by creating a C# code on the fly, part by part by part. First the constants, then the parameter, then the method call, then the lambda, and then I can invoke that method. And here it is. The result of the method is right here. Here it is. I created a delegate on the fly during the code execution and not compile time. This technique can be quite useful in certain circumstances, and it can be useful to optimize code which uses reflection directly. Expression trees may be faster. You need to measure, depends on the case, but a lot of times you need to, when you use expression trees, it will be faster than plain auto reflection, but it depends on the case. And pretty much that's it. We learned how to analyze expression trees, and you always analyze expression trees like this. You check the node type, then cast it and extract information. Check the node type, cast it, extract information. For example, the examples I showed you from my framework, if I go to utilities, so it's abstraction, source abstractions, utilities, expression parser, you see that here I'm doing essentially the same algorithm. I check for the node type, I cast it, I do something. I check for the node type, I cast it, I do something. I check for the node type, I cast it, I do something, and so on. And besides analyzing expression trees, we also learned how to create expression trees on the fly. You can create a lot of different types of code. If you use expression trees, you can create for loops, you can create member initialization, array creation, actually whatever you like. So it's a useful tool to know. Okay guys, that was it for this video. Stay tuned for the next one, which will be uploaded in a couple of days, where I will be showing how to use expression trees in your web application code, and it will save you some usage of magic strings here and there, and your controllers and your C# compilation will be very happy from that. If you like this video, hit the thumbs up button, subscribe to this channel. I'm trying to upload new videos every week, one or two depending on my schedule. If you are writing ASP.NET Core applications, take a look at my libraries. You can also take a look at the old ASP Web API 2 framework. I have a library for that too. And you may try to contribute, you may start the repo, fork it, watch it for releases, whatever you like. Additionally, all my projects are supported in Patreon, Open Collective, PayPal, and Buy Me Coffee. So if you want to really help me, whether it's for the videos or for these projects, or you find them useful, or just like .NET in general, you can become a backer here. Some people already did, and you have my eternal gratitude. All contributions are written in the backer MD file, and you will stay here essentially forever. If you continue to support my projects, you will be listed here. When you decide to stop for whatever reason you like, I will list you in previous supporters. Thank you very much guys, and bye.